roughly 500 million years after the universe was born, when space-time itself had barely emerged from the endless shadows of creation, something occurred that should not have been possible. Astronomers using the James Webb Space Telescope detected around 300 unusually brilliant celestial structures that behave like mature galaxies, even though they existed at a time when the cosmos was only a small fraction of its current age. These objects blaze in deep red tones in the infrared spectrum, and their glow suggests they contain enormous populations of stars, far too many, far too early. According to every accepted timeline of cosmic evolution, such massive concentrations of matter should have required hundreds of millions of additional years to take shape. The dark matter that forms the invisible backbone of all galaxies had barely begun clumping together. Hydrogen gas should have remained so thick and light-absorbing that starlight could not escape, yet there they were, shining defiantly across the abyss of time. To grasp how astonishing this is, imagine a newborn baby speaking fluently within minutes of birth. That metaphor captures only a fraction of the absurdity these findings present. Researchers at the University of Missouri examined 4 small windows of seemingly empty space, only to reveal clusters of objects shining many times brighter than anything expected at those distances. They are not faint smudges or insignificant anomalies. They appear to be massive star systems, already fully formed when the universe itself was barely learning how to make light. The deeper we look into space, the further back in time we're observing, because light needs time to travel. Every beam of light collected by telescopes has been on a long journey across expanding space. These newly discovered objects are so distant that the light we see today left them when existence was only between 500 and 700 million years old. Compared with our current cosmic age of 13.8 billion years, that era lies just beyond the universe's infancy. Traditional cosmological models insist that galaxies must grow slowly. Gas clouds collapse under gravity, forming first small stars and tiny clusters, then merging into larger systems over hundreds of millions or billions of years. But these objects refuse to follow those rules. Light from them reveals stellar masses approaching those found in today's Milky Way, which itself developed over more than 13 billion years of cosmic history. It is as though someone planted fully grown forests the moment the soil cooled enough to exist. The galaxies Webb spotted are so unexpected that scientists hesitate to even call them galaxies. The lead astronomer describes them as candidates, because more precise spectral measurements are necessary to confirm their structure. In Webb's images, they appear as small crimson pinpoints, but their brightness indicates immense energy output consistent with large, densely packed star populations. They pose a direct challenge to the LCDM, Lambda Cold Dark Matter, model, our most successful theory describing how tiny quantum fluctuations after the Big Bang gradually formed planets, stars, and galaxies. According to that framework, small systems form first, then merge to create larger ones, but these luminous structures flip that logic upside down. They suggest that giant galaxies could appear almost immediately after the first light reached the universe, which implies the early cosmos may have been more chaotic, more creative, and more extreme than scientists imagined. Interestingly, more than 80% of the observed objects fall into a class known as extremely red galaxies. Their intense redness in infrared wavelengths tells astronomers that they reside extraordinarily far away and that their light has been stretched dramatically. But at the same time, this redness hints at complex processes inside them, such as dust-rich environments or advanced stellar populations that should not have been present so soon after the Big Bang. It raises a profound question. What force or mechanism made galaxy formation race forward faster than physics currently allows? For hundreds of millions of years after the universe became transparent, no stars existed to fill the void. This period, often called the Cosmic Dark Ages, represents a time when hydrogen gas and dark matter silently drifted through a black and frozen universe. Before galaxies like these could even begin to form, the first stars had to ignite and transform the cosmos forever. And yet, not long after that first sparkle of starlight, 300 enormous star systems were already blazing, as though the universe had skipped crucial steps in its own evolution. No one expected the dawn of galaxies to be this bright. In one stunning discovery, James Webb has turned our understanding of the early cosmos from a confident narrative into a deep, unanswered mystery. Something extraordinary, perhaps entirely new to science, must have been shaping the young universe, sculpting giants in record time while our models insist they had no right to exist. When astronomers first saw these massive ancient objects glowing at the dawn of time, the immediate reaction across the scientific community was disbelief, because their existence breaks nearly every step-by-step rule we thought we understood about how galaxies grow. According to the physics that governs cosmic structure formation, the earliest stars should have been small, unstable pioneers scattered in tiny miniature galaxies, not huge, mature systems bursting with billions of suns. Everything about these candidates implies that the universe either evolved much faster than our current models predict, or that something fundamental in our understanding is incomplete. The timeline is the core of the paradox. From the moment of the Big Bang, the universe needed hundreds of millions of years to form neutral atoms, then even more time to gather those atoms together into the first dense clouds capable of making stars. Only after many cycles of star birth and explosive star death could enough heavier elements form for complex galaxies to exist. But these newly detected objects already possess large stellar masses at a time when that enrichment process should barely have begun. It is as though the cosmic story jumped ahead several chapters without warning. Our standard cosmic blueprint, the LCDM model, lays out an orderly and slow assembly line. The smallest dark matter halos collapse first, then merge into slightly larger ones, and so on through countless generations. In this picture, tiny galaxies gradually merge into larger galaxies through collisions, producing bigger and brighter star systems over billions of years. But the Webb discoveries imply that giant galaxies were already present almost right after the cosmic clock started ticking. These structures seem too large and too luminous to have grown from anything resembling the slow, hierarchical process at the heart of LCDM. Another angle of the puzzle concerns the universe's invisible architecture: dark matter. Without dark matter, halos to provide gravitational scaffolding, gas cannot gather densely enough to initiate star formation. But simulations show that massive halos simply did not have enough time to form by the age represented in the Webb observations. Even in regions that began slightly denser due to early quantum fluctuations, growth should still have been gradual. Instead, these objects suggest dark matter, either clumped together far more efficiently than expected, or that completely unknown gravitational processes were in play. Beyond halo formation, there is the issue of baryonic or ordinary matter. After the Big Bang, hydrogen and helium gas filled the universe, but it was spread extraordinarily thinly across space. You might compare it to having the ingredients for a skyscraper dusted lightly across an entire continent. Gathering enough material to build a massive modern-sized galaxy in just 500 million years requires inflow rates far beyond what observations and simulations suggest are possible. That means either the gas moved faster and more decisively than our physics predicts, or there must have been much more matter available in certain regions than theory accounts for. Star formation itself adds another complication. The earliest stars, known as population 3 stars, formed from pure primordial gas with no metals. In astronomy, metals refer to all elements heavier than helium. These first stars were likely enormous and short-lived, exploding in supernovas that seeded space with heavier elements necessary for forming new generations of stars. But this recycling process should have taken multiple generations to produce enough heavy elements for galaxies of the size Webb observed. Yet the newly found objects appear to already possess complex stellar populations, implying multiple cycles of star birth and death compressed into a timeline that leaves very little room for such evolution. In essence, these galaxies represent a cosmic speedrun that should not be possible. Their brightness presents yet another puzzle. The intensity of light emitted from these distant objects is typically associated with galaxies that have been forming stars rapidly for a long time. But young galaxies should be messy, chaotic, and inefficient. Stellar winds and exploding stars blast gas outward, reducing the fuel available to form new stars. It is a self-limiting process. To maintain the kind of sustained, rapid star formation implied by the observations, these systems must have somehow overcome the feedback mechanisms that normally slow galactic growth. This hints at exotic conditions in the early universe that allowed gas to collapse more effectively or remain bound despite destructive forces. Dust content is also bewildering. Dust is created by stars when they die, and it absorbs blue light while letting red light through. contributing to the deep infrared coloration of galaxies. If these objects contain dust, which many appear to, it means multiple generations of stars had already lived and died very quickly. That would push the beginning of significant star formation even closer to the Big Bang, possibly within the first 200–300 million years of cosmic history. Until now, astronomers believed that such rapid enrichment was impossible. Taken together, these contradictions paint a picture of a universe-forming structure with intense urgency, almost as if some unknown accelerator had pushed galaxies into existence far sooner than nature should have permitted. Each new measurement intensifies the mystery rather than resolving it. Webb has effectively shown us that our confident understanding of the universe's earliest chapters is an illusion, and the truth is far more dynamic, extreme, and unexplained than we ever imagined. These primordial giants stand as a direct challenge to cosmic evolution as currently taught, forcing scientists to rethink nearly every assumption about the birth of galaxies. Until we can explain how vast star systems emerged in such a short time, the foundations of cosmology remain shaken. One of the most striking features of these ancient galaxy candidates is their deep, intense red coloration, which has become central to their identification and interpretation. More than 80% of the objects detected by Webb fall into a category astronomers refer to as extremely red galaxies, a label that carries significant scientific meaning. The redness is not simply a matter of artistic description. It serves as a cosmic fingerprint revealing both their age and their distance. In a universe that has been expanding for billions of years, light behaves like a messenger that ages along the journey. Photons emitted as bright blue or ultraviolet radiation from young energetic stars gradually stretch into longer, redder wavelengths as the space they travel through expands. By the time that light arrives at our telescopes, billions of years later, it has been transformed into infrared radiation. This phenomenon, known as redshift, provides a direct way to measure how far away something is and how far back in time we are observing. The higher the redshift value, the closer we are to witnessing the cosmic beginning. The galaxies discovered by Webb exhibit redshift levels so extreme that their light must have originated in the universe's first few 100 million years. Their intense colour signals that we are looking not just far, but impossibly far, into the depths of time. However, redshift alone does not account for everything we see. The brightness and specific colour signatures of these galaxies suggest that their redness comes not only from distance and cosmic expansion, but also from internal physical processes. One likely contributor is tiny solid particles made of carbon, silicon and metals produced by stars when they die. In modern galaxies, dust absorbs blue light more effectively than red, allowing red wavelengths to escape more easily. That means a dust-rich galaxy naturally appears redder. But dust cannot exist without multiple generations of stars living and dying, because the first stars contained only hydrogen and helium. The presence of dust in these early galaxies would imply that several waves of star formation had already occurred within an extremely short period of time. In other words, these galaxies would need not only to have formed stars rapidly, but to have recycled those stars through supernova explosions almost immediately afterward. Another possible explanation involves the ages of the stars inside them. As stellar populations mature, the hottest and bluest stars die first, leaving behind cooler, redder stars. In most galaxies, this transformation takes hundreds of millions to billions of years. Yet here we see objects that already seem to contain older, more evolved stars at a time when, by standard computation, the universe was barely old enough to create stars at all. That contradiction intensifies the mystery. How could star populations age so fast that we see the fingerprints of maturity in a universe still learning to shine? And if they did not age faster, what unknown phenomenon is making them appear older than they should be? There is also the possibility that some of these extremely red objects may not be galaxies in the traditional sense. Instead, they could be powered by actively feeding supermassive black holes surrounded by swirling disks of gas that heat up and radiate immense infrared energy. Such active galactic nuclei can outshine the rest of the galaxy combined, producing a brightness that mimics large stellar populations. If these objects are indeed harbouring supermassive black holes, then we face yet another huge scientific paradox. How could black holes with millions or billions of solar masses already exist so early when there should not have been enough time for even small stars to collapse into black hole seeds. Every interpretation leads to a new violation of established cosmic logic. Astronomers must therefore tread carefully, considering multiple explanations simultaneously while gathering more data. Spectroscopy analysing the precise wavelengths of light emitted by these distant structures will determine whether we are looking at true stellar populations or energy from superheated gas around black holes. But acquiring such detailed data on faint distant objects requires long observation times and the full capabilities of Webb's instruments. Until those measurements are completed, the classification of these objects remains provisional. Meanwhile, astronomers use models to test different scenarios. If the redness comes primarily from dust, then the early universe must have undergone rapid and intense star formation followed by equally rapid star death. If it comes from aged stars, then stars must have formed almost instantly after the Big Bang. If active black holes dominate, then black holes must have grown with incredible speed, far outpacing anything seen in later cosmic epochs. None of these options fits comfortably within established cosmology, yet one or some combination of them must be true. Even the possibility that these are smaller, less massive galaxies masquerading as giants due to misinterpretation creates its own difficulties, because their brightness strongly implies large mass. There is no easy escape route from the implications Webb has revealed. The extreme redness of these galaxies is therefore more than a visual trait. It is a clue pointing toward a fundamental revision of how cosmic history unfolded. Every photon they emit challenges the chronology encoded in textbooks and simulations. What we thought would be a quiet transition from the cosmic dark ages into a slow dawn of star formation now appears to have been a sudden, explosive burst of creativity. The early universe may not have been a patient craftsman shaping structure over long ages, but rather an eager artist conjuring complexity faster than we ever imagined. These crimson beacons from the edge of time now stand as symbols of a universe that refuses to obey the rules we wrote for it. They demand new explanations, new theories, and possibly new physics to understand how the cosmic dawn could glow so brightly so soon. To understand why the discovery of massive early galaxies is so astonishing, we must first understand the era that came before them, a period known as the Cosmic Dark Ages, a time when the universe existed, but nothing in it produced light. This mysterious epoch began roughly 380,000 years after the Big Bang, when the once superheated universe finally cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before that moment, the cosmos was a glowing plasma, a thick soup of charged particles where light could not travel freely because photons were constantly scattering off free electrons. But once the universe cooled and recombination occurred, photons suddenly found themselves free to race through space unimpeded. This ancient light is now observed as the cosmic microwave background, the faint afterglow of creation. However, despite the newfound transparency, there were still no stars, no galaxies, no glowing structures, only cold, dark hydrogen gas spread thinly across an expanding universe. Imagine an endless ocean of invisible fog stretching in every direction, silent and lightless. Space was unimaginably vast and almost entirely uniform, with tiny ripples of slightly denser matter scattered throughout. These density fluctuations were the seeds that would eventually grow into galaxies, but during the Dark Ages they were merely subtle hints of future structure. Gravity worked quietly but persistently, slowly pulling more matter into the denser regions. Dark matter, which far outweighs ordinary matter, played the leading role here. Invisible and enigmatic, it formed enormous halos gravitational wells that would someday become the birthplaces of galaxies. But at this early time, even dark matter needed more time to assemble significant structures. Everything was happening at a pace that, in theory, should have prevented massive galaxies from forming in the blink of an eye cosmic moment that Webb now shows us. Temperatures in this epoch dropped to nearly absolute zero. Hydrogen gas cooled to around 450 degrees Fahrenheit, leaving the universe not only dark but frigid and still. There was no starlight, no heat except for the faint and fading warmth left over from the Big Bang. For hundreds of millions of years, this was the cosmic status quo. Expanding space filled with quiet, cold gas and the silent gravitational influence of dark matter, slowly sculpting the unseen skeleton of the cosmos. Eventually, in some of the densest pockets of gas, Gravity overcame the outward pressure of the cooling hydrogen. Atoms collapsed inward until their centers ignited nuclear fusion. The first stars flickered into existence, piercing the darkness like sparks from a newly struck flame. These pioneering suns, known as Population 3 stars, were nothing like the familiar stars we see in the night sky today. They were made purely of hydrogen and helium, with none of the heavier elements produced by later generations of stars. Without those heavier elements, cooling was less efficient, and star formation proceeded differently, resulting in colossal giants, likely hundreds of times the mass of our Sun. They blazed fiercely, burning their fuel with reckless speed. Their lives were brief, lasting only a few million years before exploding in cataclysmic supernovas. Yet despite their short existence, they transformed everything. Their brilliant ultraviolet radiation began breaking apart the surrounding hydrogen atoms in a process called reionization, turning the dark universe transparent once again. Their supernova explosions scattered newly forged heavy elements, carbon, oxygen, silicon into space, enriching the interstellar medium and enabling a new style of star formation. In this way, the first stars acted as both the light bringers and the architects of future complexity. They lit the sky and chemically prepared the universe for the kinds of stars, planets, and galaxies we know today. But here is the crucial point. Reionization and chemical enrichment should have unfolded gradually. According to current models, it would have taken hundreds of millions of years and multiple generations of stars for enough heavy elements to accumulate to support the formation of large, mature galaxies. The Dark Ages should have been a long, slow build-up to a gradual dawn. Instead, the James Webb Space Telescope has found powerful evidence that something far more dramatic occurred. The presence of extremely bright, massive galaxies only 500–700 million years after the Big Bang suggests that this cosmic awakening was not a slow sunrise, but a sudden explosion of light and structure. The Dark Ages, therefore, present a rigid bottleneck in cosmic history. There simply should not have been enough time between the first stars flickering on and the rapid emergence of fully developed galaxies with billions of stars. If Webb's findings are confirmed, then some mechanism we do not yet understand allowed matter to gather and form stars astonishingly quickly inside those early dark matter halos. Perhaps gas cooled more efficiently than expected. Perhaps the first stars collapsed into black holes that rapidly fed on surrounding matter. Perhaps unknown physics accelerated the assembly of structure. Whatever the explanation, these newly discovered objects demand that we reimagine the transition from darkness to light. The cosmic Dark Ages were supposed to be a time of quiet waiting, of slow gravitational sculpting, but the universe we are now seeing appears restless and ambitious from the very beginning. What once seemed like a tranquil, empty chapter now looks more like a pressure cooker, ready to erupt into brilliance. And Webb's discoveries imply that the universe wasted no time at all in filling itself with light. The end of the cosmic Dark Ages came not with a slow transition, but with the sudden ignition of the first stars, monumental beacons that forever reshaped the destiny of the universe. These earlier suns, known to astronomers as Population 3 stars, emerged from primordial hydrogen and helium that had been cooling and collapsing inside growing wells of dark matter. Unlike the stars we see today, which contain a mixture of heavy elements produced by previous generations of stellar life, these originals were chemically pure, forged from the simplest ingredients the cosmos had to offer. The lack of heavy elements drastically changed how they formed, causing them to grow to extraordinary sizes. Many models suggest they reach masses 100 times greater than that of our Sun, possibly even pushing up toward 1,000 solar masses. They burned with unbelievable intensity, blazing blue-white with temperatures far hotter than any modern star could sustain. Their lifespans, however, were incredibly short, just a few million years, the cosmic equivalent of a lightning flash. Yet in that fleeting moment, they acted as the catalyst that transformed the universe from a cold, dark, and chemically primitive expanse into a vibrant, illuminated, and increasingly complex environment. These cosmic giants released immense amounts of ultraviolet radiation, energetic enough to rip electrons away from hydrogen atoms in the surrounding gas. This radiation marked the beginning of the epoch of reionization, a crucial turning point when the universe transitioned from being filled with neutral atoms that blocked light to being transparent once again. Bit by bit, their searing light carved away the darkness like torches in a vast cavern. Even more dramatic were their deaths. Roughly 3 to 10 million years after they ignited, their nuclear fuel ran out and their massive cores collapsed. Some exploded in titanic supernovas that scattered the first heavy elements throughout their surroundings, creating the foundational materials for everything from rocky planets to the chemistry of life itself. Others may have collapsed directly into black holes, seeding the universe with compact objects that later grew into the supermassive black holes now found at the centers of galaxies. Every atom of carbon in our cells, every molecule of oxygen we breathe, every speck of iron in a meteorite, these all originated from the fiery deaths of the first stars. Without them, the universe would still be nothing more than an endless ocean of hydrogen and helium. But despite their significance, these primordial stars have never been directly observed. They were simply too far away, too early, and too short-lived. Their existence is inferred from models, from the chemical fingerprints of later generations of stars, and from the structure of the universe that emerged in their wake. The James Webb Space Telescope, however, is now capable of glimpsing indirect clues about them. In some of the extremely bright early galaxies Webb has found, astronomers see hints of intense ultraviolet radiation and patterns of starlight that could be consistent with population 3 influence. If confirmed, these galaxies would not merely contain second-generation stars, they may hold the fading glow of the earliest stellar titans themselves. The speed with which these first stars ignited adds another layer of shock to the current cosmic puzzle. Standard theory suggests that the densest regions of gas took hundreds of millions of years to reach the conditions needed for starbirth. Yet Webb's discoveries imply that vast regions of the early universe had formed stars nearly as soon as it was technically possible. Such rapid star formation requires efficient cooling of gas clouds, but without heavy elements, cooling should have been slow and difficult. Something perhaps turbulence, dark matter effects, or exotic physical processes must have accelerated the collapse of matter. The fact that dust and chemically enriched material appear to exist in some of the earliest observed galaxies means population 3 stars must have lived and died extremely quickly, undergoing multiple cycles of star creation and destruction in what feels like an impossibly compressed timeline. And that brings us to a deeper implication. The emergence of the first stars may not have been an isolated spark, but a cosmic wildfire. Once one region of gas ignited, radiation from those initial stars may have influenced neighbouring regions, encouraging faster collapse and more starbirth, creating a cascading wave of illumination sweeping across the universe. The first stars, therefore, were not just passive milestones in an unfolding story, they were active agents driving the cosmic dawn. Their ferocity shaped the formation of galaxies, altered the behaviour of gas, and set the stage for every structure we observe today. At the same time, they remain one of the most elusive mysteries in astronomy, hidden behind staggering distances and the faintest whispers of ancient light. And now, as Webb reveals massive galaxies shining far earlier than predicted, the first stars move even more centrally into the scientific spotlight. They were clearly more powerful, more abundant, or faster forming than theory allows. Something about them was extraordinary enough to reshape the universe almost instantaneously. Whatever happened in those early moments, the universe went from silent darkness to dazzling brilliance at a speed that strains the limits of our imagination and challenges everything cosmologists believed was possible. To understand why these newly detected galaxies are so shocking, we must fully appreciate how telescopes like James Webb allow us to look back in time. In space, the speed of light serves as a universal time limit. Light travels incredibly fast, about 186,000 miles per second yet on cosmic scales. That speed becomes surprisingly modest. When we observe distant stars and galaxies, we are not seeing them as they are now. We are seeing them as they were when their light first began its journey toward us. The nearest star outside our solar system is more than 4 light-years away, meaning its light takes 4 years to reach Earth. The light arriving in our eyes tonight left that star around the time we were living through a different season. Extend that distance to entire galaxies, and we are suddenly looking thousands, millions, or even billions of years into the past. The James Webb Space Telescope is not just a camera. It is a time-viewing machine capable of capturing light that has been travelling since the earliest cosmic epochs. When Webb detects objects 13 billion light-years away, It is revealing scenes from an era when the universe was still in its infancy. But the story does not end there, because space itself is not a static stage. Since the Big Bang, the fabric of the universe has been stretching outward in every direction. Galaxies are not merely moving away through space. The space between galaxies is expanding, carrying them with it like raisins embedded in rising dough. As space expands, so does the light travelling across it. The wavelengths of that light grow longer, shifting from the energetic blue and ultraviolet regions of the spectrum into the red, and eventually into infrared. This stretching of light is called redshift. The greater the redshift, the farther the object, and the farther back in time we're observing. Redshift acts like a cosmic timestamp, encoding the age of the universe at the moment the light was emitted. Astronomers can measure this shift precisely and use it to calculate distance and age. For example, when Webb observes objects with redshift values above 10, that means the light left those galaxies when the universe was less than 500 million years old. Hubble, while revolutionary in its own right, was limited because it primarily detects visible and ultraviolet light. The most ancient galaxies emitted blue-white starlight that has since been stretched into the infrared far beyond Hubble's capabilities. Those galaxies were literally invisible to its instruments. Webb, however, was built specifically for this purpose, equipped with ultra-sensitive infrared detectors designed to hunt down the faint ancient light that has been shifted by the expansion of space. That is why Webb is now revealing entire populations of early galaxies that Hubble had no ability to see. The physics here creates a fascinating paradox. The farther away an object is, the older the light we observe. Yet because the universe's expansion is accelerating, the most distant galaxies are also receding the fastest. Their redshift becomes so extreme that the light they emitted as blazing young stars now arrives as faint infrared whispers stretched across billions of years. Webb's instruments can detect wavelengths between 0.6 and 28 micrometers, exactly the range required to observe the universe at ages we have never glimpsed before. But redshift is not the only complication. Because space has expanded over the billions of years that the light has been travelling, the galaxy that emitted that light is now dramatically farther away than its look-back distance would suggest. A galaxy that appears to be 13 billion light-years away in terms of look-back time is now, due to expansion, over 30 billion light-years distant in actual current separation. This means Webb is not just peering across space, it is capturing light from regions that are now far beyond what we could ever reach physically, even travelling at the speed of light. The early universe is now locked behind an expanding horizon. These extreme distances explain why observing the cosmic dawn has always been such a daunting challenge. The light is incredibly redshifted, incredibly faint, and buried in a universe filled with other radiation that can obscure or confuse the signal. Webb's massive 6.5-meter mirror is designed to collect as much of that ancient light as possible, pulling from the darkness photons that have been travelling nearly the entire history of time. This capability has now given us a front-row seat to a chapter of the universe we once believed forever inaccessible. The shock of Webb's discoveries stems from the expectation that, once we could finally see the earliest galaxies, we would discover small, primitive structures, cosmic toddlers just learning to walk. Instead, we found giants fully grown while the universe was still learning how to form stars. That light, travelling across 13 billion years of cosmic history, tells us a story that does not match the one we wrote from theory. Every deep-field Webb image functions as a time capsule, carrying messages from a past where nature apparently moved with astonishing speed. That is the power of redshift. It allows the universe to reveal its secrets, but only if we are willing to revise our understanding when those secrets defy expectation. And now, confronted with massive bright galaxies appearing impossibly early in time, cosmologists must wrestle with a new reality. Light has shown us a universe we thought we understood, yet clearly never fully did. Before the launch of the James Webb Space Telescope, astronomers believed they already possessed a strong understanding of the universe's earliest galaxies, thanks to observations from the legendary Hubble Space Telescope. Hubble had detected several extremely distant galaxies, but they appeared faint, small, and low in mass, just what theories predicted for that era. These early detections gave scientists the impression that the first galaxies were tiny seeds that would gradually grow into the majestic structures seen in the modern universe. Nothing Hubble ever observed suggested that huge galaxies could have existed so soon after the Big Bang. It turns out the reason Hubble failed to find them was not that they were absent, it was that they were invisible to its instruments. Hubble primarily observes ultraviolet and visible light, the types of light emitted strongly by new young stars. However, over billions of years of travel, that light becomes stretched by the expanding universe. Ultraviolet becomes visible, visible becomes red, and eventually the wavelengths shift completely into the infrared portion of the spectrum, far beyond Hubble's detection capability. Even though these early galaxies were incredibly bright when their light was first released, by the time that light reached Earth, it had transformed into faint infrared radiation. To Hubble, they were essentially ghosts. The most distant galaxies Hubble detected were at redshift values around 7 or already impressive, but still far from the record-shattering distances that Webb now probes. At those redshift levels, the galaxies Hubble found were small and unassuming, containing only a tiny percentage of the mass of modern galaxies. These discoveries led to a widespread belief that massive galaxies did not form until many hundreds of millions of years later. If Hubble could see only the cosmic toddlers, astronomers assumed the giants simply did not yet exist. James Webb was designed to shatter that blind spot. With its enormous 6.5-meter mirror and highly sensitive infrared instruments, Webb can detect wavelengths between 0.6 and 28 micrometers, exactly the range where ancient redshifted starlight now resides. Its detectors are cooled to extremely low temperatures to eliminate thermal noise that would otherwise drown out faint signals. Webb's instruments are so powerful that they can detect a handful of photons that have been travelling through expanding space for nearly the entire age of the universe. This capability has exposed a stunning realization. The early universe was far busier than anyone assumed based on Hubble's incomplete picture. What once looked like a sparse and gradual cosmic dawn now appears vibrant and crowded with unexpectedly mature structures. Hubble's limitation was not just in wavelength sensitivity but in depth. Even when it pushed to its deepest fields, Hubble struggled to gather enough faint infrared light to see anything more than the smallest early galaxies. Webb, with its far superior light-collecting ability, can stare much deeper into the darkness and reveal galaxies dozens or hundreds of times more massive than the ones previously detected. Another key difference lies in resolution. To distinguish a distant galaxy from a star or other object, the telescope must resolve its structure. Light that has travelled billions of years spreads out and becomes harder to focus. Hubble's smaller mirror and shorter wavelength limitations meant that many distant objects simply appeared as faint blurs indistinguishable from background noise. Webb, with larger optics and infrared vision, captures sharper detail at much greater distances, allowing astronomers to identify brightness patterns that strongly indicate large structured galaxies. Webb's discoveries not only expanded our view, it corrected a bias. For years, scientists assumed their models must be correct because Hubble's observations matched expectations. Yet as soon as better observational tools became available, the universe revealed that those expectations were far too conservative. Hubble gave us the first glimpse of the cosmic dawn, but Webb is now showing us that dawn was not dim and slow, it was intense and full of life. The fact that Hubble missed this population of early giants is not a failure, but a reminder that each generation of technology opens a new layer of cosmic truth. For over 30 years, Hubble revolutionized our understanding of time, distance, and structure in the universe. But it was simply not equipped to penetrate as deeply into the infrared realm, where the first galaxies now hide. Webb is that missing key. By unlocking this hidden region of the spectrum, it has revealed a chapter of cosmic history we never imagined. Massive galaxies forming at breakneck speed, while the universe was barely out of darkness. In a way, Hubble allowed us to write the opening pages of the universe's story, but it left entire chapters blank. Webb is now filling those pages in, and the narrative is nothing like what we thought. It is a reminder that scientific confidence often depends on the limits of our vision. When our eyes improve, so does the universe's ability to surprise us. To understand why the existence of massive early galaxies is such a profound challenge, we must scrutinize the cosmic inventory available in the first few 100 million years. After the Big Bang, the universe consisted almost entirely of hydrogen and helium gas, with a tiny trace of lithium simple elements formed during the first few minutes of existence. Everything else, every heavier element that builds planets and life did not yet exist. Ordinary matter made up only a fraction of the cosmos, while the vast majority of mass was locked up in dark matter, a mysterious substance detectable only by its gravity. Although dark matter dominated the structure-forming process by pulling gas into clumps, it could not form stars or planets on its own. The gas was spread astonishingly thin, even in regions that would later host galaxies. When cosmologists simulate the early universe, they find that gas density across space was so low that gathering enough material to form massive galaxies should have taken billions of years. Instead, Webb has shown us galaxies containing tens or even hundreds of billions of solar masses worth of stars within just a few 100 million years. It is like discovering fully built skyscrapers in a desert where the ingredients for concrete have barely been invented. The question imposes itself sharply: where did all that mass come from so quickly? Gravity acted as the grand architect, pulling hydrogen and helium into denser regions, but gravity works slowly, especially on vast scales. Even in the densest primordial pockets, simulations indicate that only small structures, tiny proto-galaxies, should have formed at first. Larger ones would emerge later through countless mergers. Yet Webb's galaxies are not tiny fragments. They are already incredibly luminous and massive. This implies that either these regions started with an unusually high concentration of matter, or that some mechanism greatly accelerated the condensation of gas into stars. One hypothesis suggests that these galaxies formed in extremely rare cosmic landscapes, statistical outliers, where matter density was far above average due to random quantum fluctuations in the first fraction of a second after the Big Bang. In these fortunate pockets, dark matter halos might have grown faster, drawing in ordinary gas at accelerated rates. But even this explanation has severe limits. Simulations show that such density peaks should be exceptionally scarce, perhaps enough to explain a handful of unexpectedly early galaxies, but not hundreds of them discovered across one modest survey area. Webb did not detect a single anomaly. It found a large population. That suggests the universe was producing massive systems rapidly and efficiently, not by chance alone. Another major obstacle involves the process of turning gas into stars. Gas clouds resist collapse due to pressure, and they require cooling to condense into dense stellar nurseries. In the modern universe, heavy elements in gas act as cooling agents, helping energy radiate away to allow gravity to dominate. But early gas lacked metals entirely, meaning cooling should have been slow and insufficient to support fast star formation. Standard theory says that the earliest stars likely formed singly or in small clusters, not huge swarms creating billions of stars in a short span, and yet that seems to be what happened. Moreover, star formation is inefficient. Even in the most active starburst galaxies today, only a small percentage of available gas becomes stars before energy feedback, winds from young stars, radiation pressure, and supernova explosions, blows much of the gas back into space or heats it, preventing further collapse. Present-day galaxies lose tremendous amounts of potential star-forming material, but these ancient galaxies appear to have achieved unbelievably high formation efficiency, potentially using up nearly all available gas almost as soon as they gathered it. They act like cosmic vacuum cleaners, sweeping their regions clean and locking matter into stars at a pace unseen anywhere else in known cosmic history. Furthermore, modern galaxies gain much of their mass through merging with smaller neighbours. That's a slow and messy process involving repeated collisions and restructuring. But in the era Webb is observing, there simply had not been enough time for frequent mergers to build such giants. Webb's observations imply that galaxies could grow enormous without relying on lengthy hierarchical assembly. To unify all of these mass-related anomalies, cosmologists are now confronted with three possible conclusions, none of them comfortable. First, star formation physics in the early universe may have worked under extreme rules that no one anticipated, rules that allow maximum efficiency, extremely rapid cooling, and fierce gravitational collapse. Second, our understanding of dark matter's early behavior may be incomplete, perhaps underestimating how quickly halos could have grown or how strongly they could have attracted gas. Third, and most radical LCDM cosmology, the framework that has guided decades of research, may require modification or replacement. The discovery of so much mass gathered so early is forcing scientists to revisit the most fundamental assumptions about cosmic growth. In short, the early universe did not gently nurture the first stars and galaxies into existence. It appears to have rushed headlong into forming enormous, brilliant stellar cities almost immediately. The matter was there, but somehow the universe figured out how to assemble vast galactic structures with impossible speed. Until we uncover the mechanism behind this breathtaking efficiency, the cosmos remains far more ambitious and enigmatic than we ever imagined. To appreciate the scale of the mystery the James Webb Space Telescope has revealed, we must look at how galaxies are supposed to grow according to well-established astrophysical models. In the standard picture of cosmic evolution, galaxies acquire their mass gradually through two primary processes: internal star formation, where gas collapses into new stars, and hierarchical merging, where small galaxies combine to form larger ones. This dual growth path takes time, lots of time, and is controlled by physical limits that prevent runaway rapid development. In the modern universe, galaxies like the Milky Way did not appear overnight. Instead, they spent billions of years slowly gathering gas, converting only a fraction of it into stars and continually interacting with neighbouring systems. The current structure of the cosmos is the product of this long, meticulous build-up. After the Big Bang, matter clumped into small protogalaxies embedded within dark matter halos. These miniature structures, containing perhaps millions of stars at most, represented the earliest steps toward galaxy formation. Over hundreds of millions of years, they collided and merged under the influence of gravity, pooling their gas and stellar contents to form steadily larger and more complex galaxies. This hierarchical growth model is a cornerstone of the LCDM cosmological framework, and until now, nearly every observational result has supported it. For example, when astronomers observe galaxies at intermediate distances corresponding to around 5 to 8 billion years after the Big Bang, they see many irregular merging systems. The universe at that time was still assembling its great structures. Even now, galaxies continue merging. The Milky Way is currently absorbing several dwarf galaxies and is on course to collide with Andromeda in a few billion years. Growth is continuous but never instantaneous. Star formation within galaxies is likewise constrained. Gas must cool down, condense, and fragment under gravity to produce stars. But numerous feedback mechanisms act to slow this process. Young stars emit powerful ultraviolet radiation that heats nearby gas. Stellar winds from massive stars push gas outward, and when stars explode as supernovas, they inject tremendous energy back into the surrounding medium, preventing further collapse for significant periods of time. All these effects ensure that galaxies cannot convert their gas reservoirs into stars too quickly without disrupting themselves. In the Milky Way, star formation proceeds at about 3 solar masses per year, modest but stable. Even the most intense starburst galaxies seen today only manage up to a few hundred solar masses per year, and they burn through their gas so rapidly that the burst lasts for only a brief epoch before they quench themselves. This self-regulating cycle has shaped galaxy growth since the earliest epochs we previously understood. Another important contributor to galactic mass is cosmic inflow, the steady stream of cold gas funneled along vast dark matter filaments into galaxies. This process sustains star formation by continually replenishing the fuel supply as older stars die and gas is expelled. Simulations show that these inflows are vital for maintaining galaxy growth over billions of years. Without them, galaxies would quickly exhaust their usable gas and stop forming stars. Yet even with these inflows, growth should remain measured and prolonged. But here is where Webb's findings break the script. The massive galaxies it has discovered must have condensed far more matter, far faster, than the hierarchical model allows. To build the equivalent mass of a modern-sized galaxy in under 500 million years, star formation rates would need to have been 10 to 20 times higher than any starburst galaxy in the current universe, and sustained continuously over that time. That directly contradicts everything we know about feedback-regulated star formation. Additionally, their required gas supplies would have needed to arrive at extraordinary speeds, drawn into dark matter halos that theoretical models say had not yet reached the necessary size. Mergers also seem incapable of explaining the masses involved. With so little time available, there simply could not have been enough merging events to turn tiny protogalaxies into massive spirals or ellipticals. The foundational assumption that small structures form first and gradually assemble into larger ones is now under severe strain. Some have proposed that perhaps these early giants did not follow the normal merging path, but instead formed directly from the collapse of massive gas clouds, skipping intermediate steps entirely. Others suggest that dark matter may have behaved differently in the early universe, enabling halos to form and grow far more rapidly than expected. Both options push the boundaries of current physics. Without an explanation, Webb's discoveries force cosmologists to confront the possibility that galaxy formation was somehow more efficient and aggressive during the cosmic dawn than at any later time in history. Perhaps the early universe possessed physical conditions that have no parallel today. Denser environments, unrestrained gas flow, minimal feedback, or unknown mechanisms that enabled a cosmic construction boom. In the familiar universe around us, nothing like this happens anymore. The fact that such rapid, massive galaxy growth appears confined to the earliest times suggests a unique and extreme regime of physics was at work, one we have not yet discovered or properly modelled. Until we understand how galaxies gained mass at such breakneck speed, the story of cosmic evolution remains incomplete, with one of its most fundamental chapters rewritten by the light of ancient giants. To truly grasp the magnitude of the puzzle posed by the massive galaxies James Webb is revealing, it helps to compare them with the behaviour of galaxies in the present-day universe, where star formation is a regulated process governed by well-understood physical constraints. Today, galaxies form stars at rates that rarely exceed a few solar masses per year. Our own Milky Way, containing hundreds of billions of stars, currently builds new ones at a modest pace of about 1 to 3 suns annually. This rate is not determined by how much gas the galaxy contains. There is plenty of material available, but rather by the delicate balance between gravity pulling gas into dense regions and feedback from young stars disrupting that collapse. When gas clouds contract under gravity, they heat up, and if they cannot cool efficiently, they resist further collapse. Heavy elements, dust, and molecular cooling pathways help the gas lose energy, allowing star formation to proceed. But as soon as stars ignite, they push back. Radiation pressure, stellar winds, and supernova explosions blow gas outward, or heat it enough to halt further star birth. This interplay creates a natural limit. Galaxies cannot convert all their gas into stars at once, because doing so would destroy the very conditions required for star formation. In the local universe, the most extreme starbursts triggered typically by galaxy collisions can briefly produce hundreds of solar masses of stars per year. Yet even these rare events are short-lived, lasting only tens of millions of years before feedback quenches the frenzy. They burn bright and fade quickly, unable to maintain such intensity for long stretches. Modern galaxies that attempt to convert too much of their gas rapidly end up expelling vast reservoirs into intergalactic space. Quasars, for example, powered by actively feeding supermassive black holes, can generate such violent energy outflows that they shut down star formation entirely, creating what astronomers call red and dead galaxies, large and massive, but no longer able to produce new stars. Another important factor limiting star formation today is the availability of cold gas. Much of the gas in modern galaxies is heated by cosmic processes, the ultraviolet background radiation, and gravitational interactions. Hot gas has difficulty cooling and condensing into star-forming clouds, slowing the growth of stellar populations. Observations show that star formation reached its peak in the universe around 10 billion years ago, and has generally declined ever since. The cosmos today is far quieter, more mature, and less eager to produce bright young stars. When cosmologists model star formation in earlier epochs, they account for the absence of metals in primordial gas, which should make cooling slower, not faster. Therefore, star formation in the first galaxies should have been less efficient, not explosively productive. And yet Webb is showing us galaxies forming stars at a pace that pushes far beyond any known physical limit, as though the rules restricting modern galaxies simply did not apply back then. Some of the earliest galaxies discovered by Webb appear to be producing hundreds or even thousands of solar masses of stars per year, and doing so continuously for hundreds of millions of years. This level of star formation efficiency approaches the theoretical maximum. Nearly every atom of available gas must be forming stars with almost no loss. That scenario contradicts every feedback mechanism we have studied. If young stars were releasing energy in the same destructive manner they do today, the gas should have been blown apart long before such large masses of stars could accumulate, The only way galaxies could build so many stars so quickly is if feedback in the early universe was somehow suppressed or overwhelmed. Yet there is no clear physical reason why that would be the case. If anything, the first stars believed to be far more massive and violent than modern stars should have made feedback even stronger. Another proposed explanation is that early galaxies might have undergone direct gas accretion on unprecedented scales, swallowing matter so rapidly that any feedback-driven losses were constantly replenished. But even this would require dark matter halos to be unreasonably large and abundant so soon after the Big Bang. Alternatively, star formation might have occurred differently than it does now, perhaps forming stars more uniformly and avoiding the turbulent feedback-driven disruptions seen in modern galaxies. But again, simulations have never produced anything close to the efficiencies we are now observing. What Webb is showing us forces a startling conclusion. Either star formation physics in the early universe operated under entirely different conditions, or our cosmological models underestimate how fast matter could assemble into star-forming structures. The puzzle is sharpened further by the discovery of substantial dust in some of these early galaxies. Dust is largely composed of heavy elements forged in previous generations of stars. Its presence indicates that multiple star formation cycles must have already occurred, meaning that not only did the first stars form extremely quickly, they lived, died, and enriched the environment rapidly enough for the second and third generations to emerge almost instantly afterward. The timeline becomes impossibly compressed. In essence, Webb has revealed a universe where galaxies achieved galactic maturity before the universe itself learned how to slow down. Something in the early cosmos pushed star formation to the absolute limit, driving rapid, efficient stellar creation on a scale unmatched in the billions of years that followed. That alone signals that the early universe was governed by conditions or mechanisms we have not yet understood, and until we reconcile these observations with theory, our models of star formation remain broken in their earliest chapters. Another shocking piece of the early universe puzzle comes from the presence of unexpectedly massive black holes at incredibly young cosmic ages. In the contemporary universe, supermassive black holes, millions to billions of times the mass of the Sun, reside at the centers of large galaxies, including our own Milky Way. Their existence is not surprising today because they have had more than 13 billion years to grow through steady feeding and mergers. But what Webb has uncovered changes everything. Colossal black holes already thriving less than 1 billion years after the Big Bang. Even before Webb, astronomers had detected quasars, extremely bright objects powered by rapidly feeding black holes, existing just 700 million years after the universe began. These black holes were astonishingly massive, some exceeding 1 billion solar masses. Their mere presence posed a major challenge to theory, because forming a black hole big enough to power a quasar takes a long time. But now, Webb has revealed more black holes embedded inside normal-looking galaxies even earlier in history, which means supermassive black hole growth did not just begin early, it accelerated at a pace that defies current physics. To understand the problem, consider how black holes typically grow. The simplest scenario begins with the collapse of a massive star, forming what is called a stellar mass black hole, perhaps 10 or 20 times the mass of the Sun. From there, the black hole can accrete surrounding gas or merge with other black holes to grow. But accretion is limited by radiation. As matter falls inward, it heats up and emits light that exerts outward pressure, preventing additional material from easily falling in. This limit is known as the Eddington limit. Under sustained Eddington rate feeding, a black hole can double its mass every few tens of millions of years. That may sound fast, but not fast enough. Starting from 10 solar masses immediately after the first stars formed, there simply is not enough time to reach billions of solar masses by redshift 7, let alone by redshift 10 or 12. Even in the most optimistic scenario, obeying known physics, these early black holes should still be tiny. Yet Webb is finding signs that large black holes were already present in early massive galaxies. Their powerful gravitational influence affects starlight. Their activity produces distinctive radiation signatures. Their existence implies that the first black holes must have had massive seeds, or that they grew in a way that bypasses the Eddington restriction. One proposal is that some black holes formed not from stars but directly from the collapse of enormous gas clouds, so-called direct collapse black holes. These could start out with masses of 100,000 suns or more. That jumpstarts the growth process, helping them reach supermassive scales faster. But for this to work, special conditions must exist. Gas must be prevented from fragmenting into stars, instead collapsing inward as one giant object. This likely requires intense radiation from nearby hot stars, along with highly specific chemical compositions and environmental settings. While possible, these conditions are thought to be rare, yet the number of massive early black holes now being discovered suggests they would have needed to be extremely common. Another idea is that early black holes fed at super Eddington rates, consuming gas faster than should be allowed. Thick disks of matter around them might trap radiation, allowing more mass to inflate without blowing away surrounding gas. Simulations show that this could lead to rapid bursts of growth, but again, it requires fine-tuned environments and prolonged periods of ideal feeding. Meanwhile, observations tell us that the early universe was harsh, chaotic, and full of explosive feedback from violent stars. How could black holes feed so efficiently under those conditions? There is yet another complication. Black hole growth and galaxy growth are deeply linked. In the modern universe, the sizes of galaxies and their central black holes scale together in a predictable relationship. If galaxies were so huge so early, the black holes in their cores must also have grown correspondingly fast, which creates a cascade of improbabilities. The timeline becomes almost absurd. You would need massive stars to form instantly, collapse into large black holes immediately, feed at maximum efficiency without interruption, and merge frequently all before the universe was even 1 billion years old. What Webb is showing us is that black holes behaved like cosmic overachievers from the very beginning, reaching maturity while the universe itself was still a cosmic toddler. Their existence implies that either the seed black holes were far larger than expected, or that feeding mechanisms in the early universe worked with a relentless efficiency we do not see today. And if black holes grew differently, then galaxy formation and cosmic evolution as a whole must also have proceeded under radically different rules. There is even a provocative possibility. Some theorists suggest that black holes might not be the products of galaxy formation, but the triggers of it. Instead of galaxies forming first with black holes emerging later, the reverse might have occurred. The massive objects could have acted as gravitational anchors around which entire galaxies assembled. That would flip conventional understanding on its head. Whether the explanation lies in exotic physics, overlooked processes, or a fundamental revision of cosmological models, one fact is clear. The early universe was able to create and nurture colossal black holes incredibly fast, in direct contradiction to theoretical predictions. Webb has not only illuminated the first stars and galaxies, it has thrust black holes into the centre of the cosmic mystery, where they threaten to reshape our entire understanding of the dawn of structure. One of the most startling revelations from the James Webb Space Telescope is not only that massive galaxies existed incredibly early, but that they already exhibited levels of organization, brightness, and structural maturity that seem wildly ahead of schedule. In the classical view of cosmic evolution, the earliest galaxies formed as small, disordered clumps of stars' irregular shapes lacking defined structure, too chaotic and underdeveloped to resemble the spirals and ellipticals we see in today's universe. Hubble's previous deep observations appeared to confirm this expectation, but Webb's data paints a dramatically different picture. Instead of discovering scrappy little galaxies struggling to form their first stars, Webb has detected compact powerhouses radiating with intense luminosity, indicating vast stellar populations and extraordinary rates of star formation. Many of these galaxies seem to have packed enormous amounts of matter into remarkably small volumes. They are far denser than typical galaxies in the nearby universe, more like cosmic gems small in size but containing the mass of giants. Such compactness implies fierce gravitational strength and suggests that matter collapse much more efficiently than standard models allow. The stars in these galaxies are not just plentiful, they are already contributing the kind of chemical complexity one expects. Only after several stellar generations, Webb has found signatures of heavy elements, dust and complex molecules that should not exist so soon after the first stars ignited. To produce these materials, stars must have formed, lived through their full life cycles, exploded into supernovas and enriched surrounding gas, all in astonishingly short cosmic time. That implies the universe did not simply begin forming stars, it did so in a frenzied cascade that cycled through stellar life phases at record speed. Adding to the shock, many of these galaxies appear surprisingly well structured. Some show hints of orderly disks, rotational motion, and organized shapes, contradicting the notion that galactic architecture requires billions of years of mergers and gravitational settling. Instead of chaotic beginnings, these galaxies exhibit signs of stability and coherence, forcing astronomers to reconsider how quickly order emerges from primordial chaos. Their intense brightness presents another challenge. The amount of light emitted by these early galaxies implies that they contain vast numbers of massive stars. Given the short time since the Big Bang, there simply should not have been enough star-forming fuel or time to produce such luminous stellar populations through standard mechanisms. These systems shine too brightly, as though the cosmic dawn was not a gentle sunrise but a stadium full of floodlights suddenly snapping on. Current cosmological simulations produce early galaxies that are dim, small, loosely organized, and chemically primitive. The Galaxies' Webb seas are the opposite: bright, bulky, compact, and already chemically evolved. It is not a subtle deviation, it is a complete overturning of expectations. In particular, the density of these galaxies is staggering. Some contain more stars within a small radius than even the densest modern galactic cores. This raises difficult questions. How did so much gas gather and collapse so rapidly? Why was star formation so efficient, converting nearly every available atom into stars? And how could feedback from massive stars expected to blow gas outward have been so ineffective at stopping the process? The maturity of these galaxies also suggests that environments in the early universe were highly supportive of rapid organization and growth. That is strange, because the early universe should have been more chaotic, with violent radiation fields and turbulent gas that inhibit stable structures. Instead, it seems the early cosmos somehow fostered the emergence of complexity at breathtaking speed. All of this points to physical processes we do not yet fully understand. Either the first galaxies behaved fundamentally differently from those that came later, or our theoretical models are missing key ingredients that shaped the universe from its earliest moments. Some researchers speculate that dark matter might have played a more active or unusual role in concentrating matter early on. Others suggest exotic processes such as ultra-efficient cooling mechanisms, star formation modes unlike any we see today, or even interactions with new physics that have not been experimentally confirmed. Another possibility is that the growth of early supermassive black holes helped organize these galaxies from the inside out. Their powerful gravitational influence could have accelerated the condensation of matter and enforced compact structural formation. But this idea also introduces more questions than answers, since it requires black holes to already be enormous by that point in time. Whatever the underlying reason, the implication is clear. The early universe was not slow and leisurely in assembling its first major structures. It was explosively productive. Galaxies race toward maturity as if under pressure to reach stability at mass long before theories have ever allowed. These discoveries force us to confront the idea that the universe in its infancy may have been governed by a set of conditions that have no contemporary equivalent. We are witnessing a cosmos that wasted no time transforming itself into a place filled with light, structure, and complexity. In just a few 100 million years, it produced galaxies so advanced that their existence seems almost impossible. Webb's observations do not simply challenge small details, they strike at the heart of our understanding of how galaxies form, evolve, and reach maturity. And as the telescope continues to gather more light from this early epoch, we may learn that these first massive galaxies are not rare exceptions, but common actors in a universe that rushed into brilliance far sooner than we ever imagined. Another profound surprise uncovered by the James Webb Space Telescope is the unexpected level of chemical enrichment in galaxies that formed incredibly early in cosmic history. Right after the Big Bang, the universe contained only the simplest elements: hydrogen, helium, and a tiny trace of lithium. Everything else, carbon, oxygen, silicon, nitrogen, iron, and every heavier element, had to be forged inside stars. These elements are the building blocks of planets, life, and complex chemistry, and their production requires generations of stars to live and die in supernova explosions. That process takes time, because even massive stars require millions of years to reach the point of collapse. For a galaxy to contain noticeable amounts of heavier elements so early, many cycles of stellar birth and death must have already occurred. implying a rapid succession of star generations not predicted by theory. Yet Webb's spectral observations reveal that some of the first galaxies already contained dust and metals, indicating that the astrophysical factories of element creation had been running at full speed almost immediately after the first stars formed. The presence of dust is especially revealing. Dust grains form from heavy elements expelled by dying stars, and they accumulate gradually over long cosmic timescales. In the modern universe, even with billions of years of star formation, dust remains one of the more limited materials in galaxies. But early Webb observations show dust-rich galaxies emerging less than 500 million years after the Big Bang. They are not merely starting the process of chemical enrichment, they appear to be well into it. This level of maturity requires not just one generation of stars, but multiple waves of star formation, each followed by supernova explosions capable of distributing metals into the surrounding gas. The timeline becomes compressed to a degree that feels physically impossible. Heavy elements identified in these early galaxies include oxygen, silicon, and even iron, elements produced in very different types of stellar deaths. This means the early universe must have already generated both high-mass stars that explode as core-collapse supernovas and possibly intermediate mass stars that evolve into white dwarfs and later explode in type-higher supernovas. The latter type requires significantly more time to occur, suggesting that the universe's element production schedule is even more accelerated than originally feared. Furthermore, enriched gas cools more efficiently, which paradoxically makes star formation easier and faster. This creates a feedback loop. The more stars that form early and die quickly, the more the next generation can form rapidly, pushing galaxy growth into a runaway acceleration phase. This is entirely different from the star formation regulation we see today, where feedback usually acts to slow down or stop further collapse. Another breathtaking implication of such early enrichment is the potential presence of materials relevant to the later emergence of habitable environments. While life could not exist under the violent and chaotic conditions of the early universe, the ingredients required for rocky planets, carbon-rich dust, iron, silicon, were already being produced surprisingly fast. This does not mean planets formed that early, but the groundwork was being laid much sooner than models anticipated. Astronomers once believed it took billions of years for the chemical richness necessary for Earth-like planets to emerge. Now we must consider that the universe might have become chemically ready much earlier than expected. The chemical maturity observed also suggests that population of the three stars, the first generation of pure hydrogen-helium stars, must have lived and died rapidly and in enormous numbers. These primordial giants were thought to be rare and short-lived, but Webb's findings imply they might have been far more common and influential. Their explosions would have seeded the cosmos quickly, enriching gas clouds after only a single stellar life cycle. But even then, the rapidity of observed enrichment still strains belief. Some galaxies Webb has identified appear almost as chemically evolved as the Milky Way today, despite having had only a tiny fraction of the time to build their inventories of heavy elements. Theoretical models simply cannot replicate such accelerated chemical feedback. They predict far slower enrichment, constrained by available gas supply, cooling efficiency, and the time delays required for different types of supernovae. The unexpected abundance of dust also unlocks a puzzling problem. Dust absorbs ultraviolet and visible light, and re-radiates it in the infrared. This means that galaxies containing dust should appear dimmer in early stages, not brighter, yet many of Webb's discoveries are extraordinarily luminous. This contradiction challenges assumptions about both dust distribution and radiation escape in early galaxies. Perhaps dust grains in the earliest galaxies differed in composition or size. Perhaps star formation happened in clumps that expelled dust outward, reducing its blocking effect. Perhaps entirely new mechanisms for dust production were active in the early universe. Whatever the explanation, these chemically evolved galaxies shatter the expectation that cosmic metals accumulated gradually over billions of years. Instead, they tell a story of a universe that wasted no time building complexity, where the cosmic factories of elements ignited at full throttle almost as soon as the lights turned on. The cosmic dawn, it seems, was filled with furious enrichment and recycling, a fast track to creating the conditions that would one day allow for worlds like ours. And until models can account for how dust and metals emerged so rapidly, the early universe remains a chemically enigmatic place, operating under rules that we have yet to decipher. A major transformation in the early universe, known as the Epoch of Reionization, marks one of the most important turning points in cosmic history, and the discoveries made by the James Webb Space Telescope are forcing astronomers to rethink how rapidly that transformation occurred. After the universe cooled enough for electrons and protons to combine into neutral hydrogen, space became dark and opaque to high-energy ultraviolet light. This period, called the Cosmic Dark Ages, lasted for hundreds of millions of years, during which no stars or galaxies illuminated the cosmos. But when the first stars ignited, their searing radiation began tearing electrons off neutral hydrogen atoms, changing the intergalactic medium from neutral to ionized gas. As more stars formed and more galaxies emerged, this process intensified, ultimately allowing ultraviolet light to travel freely through space and making the universe transparent again. Traditional cosmological models proposed that reionization was gradual, unfolding slowly between roughly 400 million and 1 billion years after the Big Bang. It was expected to be driven primarily by small, faint galaxies, producing ultraviolet light over long periods of time, eventually clearing the cosmic fog. However, Webb's discovery of unexpectedly large and luminous galaxies existing far earlier than anticipated dramatically changes this picture. If such galaxies were already present at 300–500 million years after the Big Bang, then reionization likely began earlier and progressed much faster than previously believed. Their enormous populations of massive young stars would have produced torrents of energetic radiation capable of ionizing vast regions of space. Rather than a slow and steady transition, the process might have been more like a series of sudden, intense bursts of illumination that quickly reshaped the universe's fundamental state. Observations from Webb show strong signs of ionized gas surrounding some of these early galaxies, suggesting they were actively blasting away the remaining neutral hydrogen at a remarkable pace. The brightness of these galaxies also indicates incredibly high rates of star formation, meaning a large fraction of available gas was being rapidly converted into stars capable of driving reionization. What is shocking is not just the number of galaxies involved, but the sheer volume of ionizing photons required to complete the transformation. Reionizing the entire universe demands an enormous supply of high-energy radiation, and until Webb's discoveries, it was unclear where that much radiation could have come from so early. Now it appears the early universe may have been filled with luminous powerhouses working together to ignite a grand cosmic awakening. However, this raises further complications. The structure of early galaxies should have been chaotic, with dense clouds of gas and dust trapping much of the ultraviolet radiation inside. For reionization to progress quickly, a significant fraction of that radiation needed to escape into intergalactic space. In modern galaxies, the escape fraction is low. Dust blocks light, and neutral gas absorbs ultraviolet photons. Yet early galaxies evidently had exceptionally high escape fractions, allowing their radiation to leak into the vast cosmic sea. That implies the early universe was more porous, or that feedback from massive stars carved out channels for light to escape more freely than models predict. The speed of reionization also challenges assumptions about the timeline of galaxy formation. If galaxies were already producing enough radiation to reshape the universe at such a young age, then the formation of stars and stellar clusters must have begun earlier than observational evidence had previously shown. Webb has detected candidate galaxies at redshifts above 12, meaning they existed less than 350 million years after the Big Bang, and some might even push beyond redshift 15, where the universe was under 300 million years old. These objects may represent the first major contributors to cosmic reionization, hinting that the process was underway almost immediately after the first stars formed. Another important implication concerns the heating of the intergalactic medium. Reionization not only made the universe transparent, it also injected tremendous amounts of heat into space, influencing how gas behaved and how future galaxies could form. Rapid heating can prevent small galaxies from forming and star-forming gas from collapsing easily. If reionization accelerated quickly, then galaxies forming afterward would have experienced a more hostile environment than previously assumed, altering their development. Webb's findings may therefore require revisions not only to the beginning of galaxy formation, but also to the entire subsequent course of cosmic evolution. The accelerated reionization scenario highlights one crucial theme: The early universe was far more dynamic and energetic than expected. Instead of a long, gradual rise from darkness, the cosmos erupted into brilliance through intense episodes of star formation and radiation. Everything unfolded with surprising urgency, as if the universe raced to illuminate itself as quickly as possible. Ultimately, Webb is revealing that Ryanization, once thought to be a slow flickering dawn, might have been a fast and ferocious transformation driven by galaxies far more massive and powerful than simulations had ever predicted. This insight not only reshapes our understanding of cosmic chronology, but also deepens the mystery surrounding the physical processes that enabled such rapid progress. How did stars form so efficiently? How did radiation escape so easily? Why did complexity emerge at breakneck speed in an era once considered primitive and quiet? Until we can answer these questions, the true nature of the universe's first light remains one of the most compelling scientific enigmas of our time. One of the foundational assumptions of modern cosmology is that galaxies grow in size and mass primarily through hierarchical merging. Small structures form first, then collide and combine over time to build larger ones. This process is central to the LCDM model, where dark matter halos merge repeatedly, drawing in gas and stars from smaller systems and gradually assembling the massive galaxies we observe in the current universe. But the incredibly early appearance of giant galaxies revealed by the James Webb Space Telescope is putting severe pressure on this idea. For mergers to explain the size and brightness of these early giants, countless smaller galaxies would have needed to form extremely quickly after the Big Bang, then collide at a furious rate, stacking their stellar masses into enormous structures, all within a few 100 million years. That scenario is extraordinarily difficult to reconcile with what we know about cosmic evolution. First, there simply should not have been enough galaxies available to merge so early. Simulations show that the early universe was sparsely populated with small protogalaxies, each containing relatively few stars. These systems were scattered across expanding space, requiring enormous time for gravitational attraction to draw them together. The distances involved and the slow behavior of gravity mean that mergers take hundreds of millions to billions of years to complete. Yet Webb is observing galaxies that appear fully assembled when the universe was barely entering its first major growth phase. Second, the merging process is inherently chaotic and destructive. When galaxies collide, gas is shocked, heated, and often expelled. Feedback from vigorous star formation and active black holes can blast material into intergalactic space, reducing the efficiency of mass buildup. In the modern universe, merging events can trigger starbursts, but these are brief and energetically disruptive, making it difficult for galaxies to retain enough gas to sustain further growth. Webb's early galaxies, however, show signs of sustained star formation and dense, compact structures, not the messy aftermath typical of repeated violent collisions. If they were assembled through mergers, those collisions must have been unusually gentle and extraordinarily efficient, a combination not supported by any theoretical model. Third, merging galaxies tend to exhibit irregular shapes with tidal tails, distortions, and scattered star clusters. Yet many of the galaxies Webb sees at very high redshift appear surprisingly orderly, showing smooth light profiles or disk-like rotation signatures that indicate stable configurations. Such organization should take far longer to establish after major merger events. This suggests that either merging played a minimal role in their growth or that some unknown mechanism allowed rapid settling into stable forms. Adding to the puzzle, Webb has revealed significant populations of early galaxies concentrated in surprisingly dense regions of space, forming what appear to be early galaxy clusters or protoclusters. These regions indicate enhanced gravitational influence and elevated merger rates, but again, too early by current expectations. For such environments to exist, structure formation must have progressed much faster than the standard model allows. The expected timeline for hierarchical merging is further strained by the need to align with the early presence of massive central black holes. If merging had driven galaxy growth, black hole interactions during those collisions would have needed to proceed without ejecting black holes from galaxy centers. Yet gravitational recoil from black hole mergers often launches them outward. In the young universe, where potential wells were shallower, retaining fast-growing black holes during mergers becomes even more improbable. Another complication arises from angular momentum. Mergers tend to scramble the rotational motion of galaxies making it difficult to form well-ordered rotating disks early on. Yet Webb has detected signs of rotation in galaxies formed just a few 100 million years after the Big Bang. Stability on that scale implies growth through smooth accretion of gas rather than disruptive mergers. Some theorists now speculate that the earliest and most massive galaxies may have formed largely via rapid, direct collapse of gas along cosmic filaments, bypassing the need for frequent collisions. In this scenario, vast rivers of cold gas could have streamed directly into dark matter halos at high rates, feeding intense star formation without the chaos of repeated mergers. But for this to happen so early, dark matter halos must have evolved much faster than models predict. Even more radically, a few researchers propose that our understanding of dark matter might be incomplete. If dark matter behaved differently in the early universe, perhaps interacting more strongly than assumed, then structure formation could have been accelerated. But such speculation would demand new physics, forcing cosmology into uncharted territory. Ultimately, Webb's findings imply that hierarchical merging, while important later in cosmic history, cannot fully explain what we are seeing near the dawn of time. The discovery of mature, massive galaxies so early suggests that the universe had a different and far more aggressive growth strategy at its beginning, one that standard theory has not accounted for. Whether that strategy involved hyper-efficient gas inflow, unusual dark matter behavior, or entirely new processes remains unknown. What is clear is that galaxy mergers, once seen as the primary driving force of galactic evolution, now appear insufficient to explain the earliest chapters of the universe's transformation. Webb has revealed a cosmos not patiently assembling itself piece by piece, but rapidly constructing massive stellar cities from the start, forcing cosmologists to rethink how the universe's greatest structures first came to be. The LCDM model, lambda cold dark matter, has served as the backbone of modern cosmology for more than 2 decades. It describes a universe dominated by dark energy, represented by L, and cold dark matter, CDM, with ordinary matter making up only a small fraction of the total content. According to this framework, structure in the universe forms gradually. Tiny quantum fluctuations in the early cosmos grow under gravity to form dark matter halos, which then pull in gas, leading to the slow emergence of stars and galaxies. This model successfully explains a vast range of observations, from the cosmic microwave background to galaxy clustering on large scales. Yet the discoveries made by the James Webb Space Telescope are forcing scientists to question whether LCDM can truly account for what was happening in the universe's earliest moments. The biggest challenge comes from timing. LCDM predicts that the first galaxies should be small, faint, and extremely rare when the universe was a few 100 million years old. But Webb has found bright, massive, well-structured galaxies in that era, common enough to show up in multiple deep survey fields. These galaxies appear billions of years older in terms of their development than the age of the universe at the moment Webb is observing them. That discrepancy implies that structure formation must have progressed far more rapidly than LCDM allows, and this is not a minor tweak. It strikes the model at its core premise, that cosmic evolution proceeds slowly from simplicity to complexity. Another pressure point is the behavior of dark matter. LCDM assumes dark matter is cold, meaning it moves slowly and clumps efficiently on small scales. But if early galaxies were so massive and well-formed so soon, dark matter halos must have assembled at breakneck speed, gathering huge amounts of mass faster than the model predicts. Either dark matter behaved differently in the early universe, or the initial conditions that seeded structure were far more extreme than our simulations assume. There is also the issue of star formation efficiency. LCDM predicts that feedback from massive stars and black holes should heavily regulate early star formation, preventing galaxies from converting most of their gas into stars. Yet Webb is showing us galaxies that apparently defied those regulatory mechanisms, turning nearly all available gas into stars rapidly and continuously. Standard simulations simply cannot produce such behavior without violating the physical assumptions that underpin the model. In addition, LCDM relies on a strict timeline for ionization and chemical enrichment, both of which must unfold slowly under its rules. But Webb shows that ionization may have been swift and driven by powerful early galaxies with surprisingly advanced chemical signatures. The presence of dust and heavy elements so early indicates a speed of stellar evolution inconsistent with what LCDM predicts. These contradictions are piling up, leaving cosmologists struggling to reconcile theory with observation. Some scientists argue that the LCDM framework may still be correct, but requires modifications that adjust the behavior of early gas cooling, star formation, or feedback processes. Others propose that dark matter might be more complex, perhaps warm, self-interacting, or possessing properties that change over time. More radical voices question whether our understanding of gravity itself might need revision. Alternative theories like modified Newtonian dynamics, MOND, have long been considered on the fringes of cosmology, but discoveries like Webb's are prompting fresh interest in whether gravity behaves differently under extreme early universe conditions. Another possibility involves the nature of dark energy. L represents a constant acceleration driving cosmic expansion. But what if dark energy evolved differently in the first billion years? Small deviations in expansion history could dramatically alter structure formation and growth rates. Even more provocative is the idea that the primordial fluctuations seeded by inflation might have been larger or more varied than usually assumed, producing denser regions that collapsed into massive halos earlier than expected. But this would require a significant revision of inflationary theory, one of the most successful aspects of modern cosmology. Perhaps the most unsettling possibility is that LCDM is correct on large scales and at late times, but fundamentally inadequate for describing the earliest epochs. Much like Newtonian gravity works brilliantly for everyday physics, but must be replaced by general relativity in extreme environments, LCDM might be a partial truth accurate for a mature universe, but not for a young one. The James Webb Space Telescope is essentially revealing the version of the universe that LCDM cannot easily explain. A cosmos that launches straight into complex structure at maximum speed. This is not a small adjustment or a patchable bug. It is a full-blown contradiction between theory and evidence. Whether this leads to tuning parameters within the model or a more revolutionary shift in cosmological thinking remains to be seen. What is undeniable is that cosmology is entering a new era, one where our most trusted model faces direct observational challenges and where bold new ideas may be required to understand how the universe truly began its story. The extraordinary speed at which early galaxies assembled has thrust dark matter into the center of the scientific puzzle posed by the James Webb Space Telescope. In the LCDM framework, dark matter is the gravitational foundation upon which galaxies form. It collapses into invisible halos that act as cosmic scaffolding, drawing in ordinary gas that eventually cools, condenses, and gives birth to stars. Dark matter makes up roughly 85% of all matter in the universe, so its behavior was expected to dominate early cosmic structure formation. However, Webb's findings suggest that dark matter halos must have formed and grown far faster than current theory predicts. If they did not, the galaxies Webb observes simply should not exist. This raises a critical question. Does dark matter operate differently in the early universe than in later times? The prevailing view is that dark matter is cold, meaning its particles move slowly enough for gravity to gather them into dense clumps. These clumps merge hierarchically, building larger halos gradually over billions of years. But the incredibly massive halos implied by Webb's early galaxies would require dark matter to cluster at unprecedented speed, reaching maturity just a few 100 million years after the Big Bang, something standard simulations cannot reproduce. One possibility is that dark matter was more interactive during the universe's earlier stages, allowing halos to collapse more efficiently. In the traditional model, dark matter interacts only through gravity, which limits how quickly structures can form. But if dark matter particles could collide, exchange energy, or clump in ways beyond gravitational attraction that might accelerate early halo growth. This idea, known as self-interacting dark matter, remains speculative, but is gaining new attention in the face of Webb's discoveries. Another hypothesis suggests that dark matter might not be entirely cold. If a fraction of it were warm, moving at slightly higher speeds, it could create a different pattern of early structure formation, possibly leading to faster halo emergence in high-density regions. Yet warm dark matter models typically predict fewer small galaxies, whereas Webb shows a surprising abundance of both small and massive galaxies early on. So while warm dark matter changes the picture, it does not obviously solve the core issue. Some researchers propose that dark matter halos in the early universe may have formed around primordial black holes, hypothetical objects that could have emerged directly from extreme density variations moments after the Big Bang. These black holes would serve as seeds for rapid halo growth, drawing in matter far faster than a typical dark matter fluctuation could. Intriguingly, this idea links two major mysteries: the origin of dark matter and the early appearance of supermassive black holes. But the existence and abundance of primordial black holes remain unproven. There is also growing consideration that our understanding of cosmic initial conditions may be incomplete. The standard model assumes that the early universe's density fluctuations, the seeds of structure, were small and nearly uniform. But if the fluctuations were larger in some regions, dark matter halos could have formed big and fast wherever matter was more concentrated. That would require modifications to inflationary theory, which describes the universe's earliest expansion. Inflation is one of the most successful components of modern cosmology, yet Webb's discoveries pressure even that foundation. Some scientists suggest that early cosmic environments may have allowed dark matter to collapse directly into extremely dense cores. Under such conditions, halos could form stars at astonishing efficiency, bypassing many of the regulatory mechanisms seen today. But what could create those conditions? That question exposes the depth of the mystery. Explanations at this level push cosmology into energy regimes and physical laws not yet observed in any laboratory or confirmed by other astronomical measurements. Compounding the puzzle is that dark matter should produce specific gravitational signatures detectable through patterns of galaxy clustering. Yet the types of galaxies Webb is finding appear more common across the early universe than models predict. That suggests rapid halo formation was not rare or confined to isolated regions, but was instead widespread, meaning the underlying cause must be something global, not just a handful of statistical outliers. There is also the issue of how gas interacts with dark matter halos. In standard theory, gas needs time to cool before collapsing into stars. Even if dark matter halos formed early, star formation should lag behind. But Webb shows stars forming almost immediately inside massive halos. This implies that either cooling mechanisms worked far more efficiently, or dark matter shaped the environment in a way that made gas collapse unavoidable and unstoppable. Ultimately, dark matter is being forced into the spotlight because its expected behavior simply cannot account for the dramatic speed and scale of structure formation revealed by Webb. If dark matter acted differently in the early universe, more interactive, more clustered, more efficient, then the entire story of galaxy formation must be revised. On the other hand, if dark matter has not changed, then our understanding of gravity or early cosmic physics must be wrong. Either answer would have profound consequences. What once seemed like a reliable foundation, dark matter dictating slow and orderly cosmic growth, now appears incomplete. The early universe obeyed rules that pushed dark matter into rapidly building the skeleton of cosmic structure. Webb has revealed that the dark sector, long treated as a background player, may actually hold the key to understanding the universe's most dramatic and poorly understood chapter, the moment when darkness transitioned into a blazing cosmos filled with stars and galaxies far sooner than anyone predicted. The James Webb Space Telescope's discoveries do more than challenge specific details of galaxy formation. They strike at the underlying physics that describe how the universe behaved in its infancy. For decades, cosmologists have believed that the early universe was governed by a predictable chain of events. Inflation set the initial conditions, cooling allowed hydrogen to form, small fluctuations grew gradually into the first structures, and galaxies slowly emerged over billions of years. But Webb's observations reveal a cosmos that leaped into complexity with astonishing haste. That forces us to ask a difficult question. Were the physical laws and environmental conditions in the early universe fundamentally different from the ones we observe today? One possibility is that the speed of growth reflects undiscovered physics operating at high energies. The early universe was incredibly hot and dense, far beyond the conditions we can reproduce experimentally. During this extreme era, forces and particles may have interacted in ways that are no longer possible. If gravity behaved differently under those conditions, perhaps stronger or more efficient at collapsing matter, structures could have formed rapidly, bypassing the bottlenecks built into current models. Some theoretical frameworks, including certain interpretations of quantum gravity and string theory, allow for variations in gravitational strength at different energy scales. If gravity was enhanced shortly after the Big Bang, the quick assembly of galaxies starts to look less impossible. Another radical idea concerns the expansion of the universe. The LCDM model assumes that cosmic expansion after inflation followed a smooth deceleration until dark energy later caused acceleration again. However, if the universe expanded at a slightly different rate in its first few 100 million years, faster or slower, that would significantly alter how quickly matter clumped together. A tiny deviation early on could lead to the colossal differences Webb is now exposing. Some researchers are exploring whether the standard timeline of expansion is incomplete, proposing alternative expansion histories or non-standard cosmologies where the universe's evolution was more dynamic than previously thought. There is also a growing interest in whether time itself might have flowed differently at the beginning. Certain exotic theories suggest that physical processes in the early universe could have occurred at altered rates due to quantum effects or varying fundamental constants. If star formation and gravitational collapse unfolded on a different temporal scale, then cosmic history might be more compressed than we imagine, making the rapid appearance of mature galaxies less surprising. Another domain under scrutiny is baryonic physics, the behavior of normal matter. Gas cooling in the early universe might have been far more efficient than standard models allow. Exotic cooling channels involving molecular hydrogen or even unknown particles could have triggered star formation almost immediately once gas collected in halos. Additionally, the first stars might have been radically different from those today, forming in enormous clusters that collapsed and recycled material at explosive speeds. These so-called population 3 stars are thought to have been massive, short-lived, and incredibly energetic. If they formed in vast quantities and died quickly, they could have jump-started chemical enrichment, black hole seeding, and galaxy growth in ways current simulations do not capture. Some theoretical physicists argue that dark energy, believed to dominate the universe today, might also have had a role earlier than assumed. If dark energy fluctuated or behaved differently in the universe's youth, it could have influenced large-scale structure or accelerated certain processes. This speculative idea suggests that dark energy might not be a simple constant, but a dynamic field with evolving effects. The role of quantum mechanics also comes into play. The early universe existed in a regime where quantum effects could shape macroscopic structures. Quantum fluctuations magnified by inflation seeded cosmic density variations. But perhaps those fluctuations were not perfectly random or subtle. If some regions were inherently denser due to quantum amplification, those patches could have collapsed into massive galaxies far earlier than average. This would imply that the seeds of cosmic acceleration and growth were planted at the very beginning, literally within the first fractions of a second. Another angle to consider is symmetry breaking, the process by which forces and particles differentiated from a more unified state. The timing and nature of symmetry breaking events could influence how dark matter, baryonic matter, and radiation interacted. A small shift in the sequence or intensity of these transitions could drastically modify structure formation outcomes. The possibility that the early universe followed a different set of physical rules is both thrilling and unsettling. It suggests that our understanding of nature, rooted in present-day observations, might not be universally applicable. Physics as we know it may be a late-time approximation, a simplified version of deeper laws that only reveal themselves under extreme conditions. Webb is not simply adding new details to an existing picture. It is showing us that the earliest pages of cosmic history may have been written using a different language altogether. The task now is to translate that language. Theoretical physicists are racing to update models, explore alternative cosmologies, and test whether new physics can bridge the gap between prediction and observation. If successful, these efforts will not just fix a problem in galaxy formation theory. They will deepen our understanding of the universe's core foundations. Webb's discoveries invite us to reconsider timeless assumptions, that physics is unchanging, that cosmic growth is gradual, and that complexity emerges reluctantly. Instead, we are confronted with a universe that jumped eagerly into structure and illumination, revealing that the rules guiding the cosmos may be far more flexible, surprising, and powerful than we ever imagined. Long before the James Webb Space Telescope opened its infrared eyes to the distant cosmos, Stephen Hawking warned that the universe might become far stranger as we looked deeper into its origins. He suggested that the earliest moments of the cosmos could reveal physics radically different from what we observe today. Laws not simply extrapolated backward from current knowledge, but new behaviors emergent under extreme conditions. Webb's discoveries seem to validate that warning. The young universe, once imagined as a primitive realm of small stars and slow progress, now appears to have been a stage of rapid transformation, astonishing complexity and intense activity. The galaxies Webb has uncovered, massive, bright, chemically advanced, intricately structured, seem wildly out of place in a universe so young. They push us toward the unsettling idea that the cosmos's first chapters do not match the story we have constructed from later epochs. Hawking cautioned that clinging too tightly to theoretical assumptions could blind us to the universe's true nature. Now, the data leaves little choice but to take his caution seriously. As we push the boundaries of observation, we are also pushing against the edges of known physics, and it is becoming clear that the early universe did not follow the familiar rules in a slow and predictable fashion. Instead, it erupted into existence with chaotic creativity, rapidly building stars, black holes and galaxies in ways that defy expectations. This tension between prediction and reality introduces an uncomfortable possibility. The universe's beginning may require new principles that we have yet to imagine. One interpretation of this strangeness is that our timeline for cosmic development is misaligned, that processes we thought took billions of years unfolded in hundreds of millions, or even less. Another idea is that our understanding of cosmic time itself could be flawed. If temporal flow was different in the early universe, faster from our perspective, then perhaps the compressed chronology we observe is not as impossible as it seems. Hawking entertained the notion that time, space, and physical laws are emergent properties, not static frameworks. In that view, asking early universe physics to behave like modern physics may be as misguided as expecting water to behave like ice. The conditions were so alien that new rules may have prevailed. The rise of supermassive black holes adds fuel to this perspective. Webb has found enormous black holes in galaxies that existed when the universe was only a few 100 million years old. Standard growth mechanisms cannot explain such monsters appearing so soon. Hawking proposed that black holes might have formed directly from the collapse of dense regions created during the Big Bang, bypassing long evolutionary processes entirely. If primordial black holes seeded the birth of galaxies, then structure emerged around gravity wells that did not require stars to exist first. Such a cosmos would assemble rapidly by design, a universe that began top-down, not bottom-up. Another startling implication of Webb's findings is that complexity did not wait for calm conditions to develop. It flourished in chaos. Heavy elements, dust grains, organized rotation, globular clusters, and massive stellar populations appeared while radiation still bathed space in high-energy turmoil. This suggests a universe wired for efficiency, almost as if it was motivated to generate structure as fast as possible. Whether driven by unknown particle interactions, alternative gravity regimes, or inflationary remnants, the result is a cosmos that looks less like a gradual evolutionary experiment and more like a rapid construction project. Hawking's work often emphasized that scientific theories must ultimately bow to observational evidence, even when those observations seem unimaginable. Today, cosmology is confronting such a moment. The familiar universe, where small galaxies merge slowly into larger ones and stars enrich the cosmos with patience, appears to be only part of the story. Behind it lies a stranger universe, one that built itself aggressively, boldly, and early. The shock astronomers feel is not just about unexpected galaxies. It is about recognizing that our intellectual comfort zone no longer aligns with reality. Webb is showing us a cosmos that may require a new paradigm, not slight modifications to existing equations, but deeper conceptual revisions. Hawking foresaw that the most profound truths about the universe might only become visible when we peered far enough back to see its origin, and that what we found there might undermine our confidence in long-held assumptions. That moment has arrived. We are seeing the universe behave like a frontier environment, where rules are flexible and transformation is instantaneous. Galaxies that should not exist do exist. Black holes too large for their era still grow. Chemistry too advanced for its age flourishes anyway. The early cosmos refuses to stay confined within traditional theoretical boundaries. Instead, it displays properties that seem intentionally tuned to produce structure quickly, raising philosophical questions as well as scientific ones. Did the universe begin with a predisposition toward complexity? Are the laws of physics evolutionary, shifting over time? Could the universe be far more self-organizing than we imagined? Hawking argued that science progresses through tension, when theory and observation collide, forcing new ideas to emerge. Webb's discoveries ignite exactly that kind of transformation. The strange universe Hawking warned us about is not hypothetical anymore. It is real, glowing from across 13 billion years of space-time, rewriting our understanding of how everything, including us, came to be. The James Webb Space Telescope has forced us to confront a profound realization. Our current story of the universe's origins is incomplete. For decades, cosmologists believed they had assembled a reliable sequence of cosmic milestones, humble beginnings marked by small stars, followed by gradual accumulation of structure and a long, steady progression toward the rich universe we see today. But Webb has peeled back the darkness of the earliest epochs and revealed a cosmos that matured far too quickly. Massive galaxies, supermassive black holes, and chemically enriched environments were already flourishing when the universe was still in its infancy. These findings challenge the fundamental principles that define modern cosmology: the growth rate of structure, the evolution of galaxies, the behavior of dark matter, and even the basic physics that governed the first billion years. We are witnessing not just a need for minor updates, but a call for a new cosmic narrative, one that embraces complexity, speed, and transformation far earlier than we ever imagined. In this revised story, the universe is not a patient architect assembling order over billions of years. It is an ambitious creator that built grand structures almost immediately, shaping itself with remarkable efficiency. Models must now account for a universe that was already bustling with energetic activity shortly after the Big Bang. Theories describing gas cooling, dark matter collapse, star formation, and chemical enrichment will require substantial revision. Some mechanisms may need to be redefined entirely. Perhaps certain assumptions, like the uniformity of early gas, the slowness of gravitational collapse, or the inefficiency of first-generation star formation, are simply incorrect. We must be open to the possibility that early cosmic environments triggered accelerated pathways toward complexity, pathways that have since become dormant or inefficient. The existence of early supermassive black holes suggests gravitational physics may involve processes we do not yet understand. Their presence hints that black holes may have formed from direct collapse of dense gas or primordial fluctuations, bypassing slow growth altogether. If so, they could have played a central role in driving the rapid organization of the early galaxies, serving not just as byproducts of star formation, but as catalysts of galactic architecture. It is equally possible that the first stars were fundamentally different from those we know now: larger, hotter, shorter-lived, and far more prolific in shaping their environment. Their explosive deaths could have recycled gas into future generations of stars with extreme speed, enriching the universe with heavy elements long before theory ever allowed. These processes may have enabled complex chemistry, the very ingredients necessary for planets and eventually life, to emerge vastly earlier than expected. That does not imply living worlds existed so soon, but it does mean the cosmos wasted no time preparing the materials required for biological potential. Webb's revelations also force us to question our reliance on extrapolation. We have assumed that the physics we measure today is the same physics that governed the early universe. But if certain laws evolved, if gravity, expansion, or particle interactions changed over time, then the familiar rules are merely a later chapter of a much larger story. This does not undermine the magnificence of the LCDM model. It simply places boundaries around its domain of validity. Just as Newton's laws remain accurate within certain regimes, but yield to Einstein under extreme conditions, the current cosmological framework may function perfectly in the mature universe while breaking down at the primordial dawn. The key now is not to discard what works, but to expand beyond it where necessary. Future models must integrate Webb's findings into a coherent theory that honors both the old successes and the new revelations. They must accommodate rapid structure formation, early chemical advancement, high-efficiency star production, and the surprising stability of young galaxies. They must allow for a universe that transitioned from chaos to complexity in record time. Most importantly, they must be willing to embrace new physics if the data demands it. Webb has shown that the cosmos is more daring, more creative, and more unpredictable than textbooks suggested. We are transitioning from a comfortable era of refinement into a bold era of exploration, where fundamental questions are once again open and exciting. How did the first galaxies gather so much mass so quickly? What ignited such furious star formation? Why did black holes emerge as giants instead of seeds? And what physical laws enable the universe to leap forward so fast? These questions are not signs of failure, they are signs of progress. Every time observation has broken theory, science has grown stronger. Webb is simply the latest instrument pushing us to deepen that growth. The universe has revealed that its earliest chapters are filled with mystery, speed, and ingenuity. Now our models must evolve to match the cosmos as it truly is, not as we once assumed it to be. The story of the universe is being rewritten, and we are witnessing the first lines of a new narrative, one where the dawn of time was not a slow awakening, but a brilliant, breathtaking burst of creation that still challenges our imagination today.